Today we're going to talk about Lesson 19, which is rational numbers. First of all, we want to define what a rational number is. A rational number, in simple words, is a fraction. The textbook talks about the idea of breaking up a whole quantity, which gives us the word fraction. It comes from the Latin word fractio, which means a breaking or a fracture. So I've created a drawing here which shows that if I had a whole green bar, it would be one whole. But I've actually divided it or fractured this segment into 6 equal parts. We have 1 6, 2 6, 3 6, 4 6, 5 6, and 6 6. As you continue on and you begin your teaching career, you're going to see that fractions typically are one of those concepts that students struggle with. So again, it's very important that they have a really good foundation with fractions. We're going to talk about the parts of a fraction. Of course, we understand that we have a numerator and a denominator that is divided by a fraction bar. A fraction bar is nothing more than our grouping symbol that separates the numerator from the denominator, but the correct terminology for that is fraction bar. The denominator, you see that I have underlined the word non-zero. It's very important to emphasize that the denominator, which is the number below the fraction bar, has to be a non-zero number. We cannot have 0 in the denominator of a fraction. That is something that you need to emphasize. 0 in the denominator of a fraction makes that fraction undefined. This denominator is going to indicate the number of parts that whole quantity has been divided into. If you go back to the drawing that we've seen on slide 1, you see that segment was divided into 6 parts. Therefore, its denominator was 6. The smallest number that we can divide a whole quantity by is 1. If you'll notice that the smallest number that you've seen on that first graphic was 1/6. So it's very important that we emphasize that denominator cannot be 0. It has to be a non-zero number. The number above the fraction bar we call the numerator. It tells me a specified part of the whole. So for instance, if I was talking about 2 6, I'm talking about 2 of those equal segments divided into 6 parts. We know that the numerator can be 0 in a fraction. If I had 0 divided by 2, that's going to give me 0. Again, the denominator cannot be 0. That makes it undefined. It's very important that students know the difference between these two concepts and that they never put 0 in the denominator of a fraction. So to simplify things, in your textbook it talks about fractions in terms of positive numbers. Here we're talking about any integer. So remember, integers are all the negative numbers, 0, and their opposites. And we must have a non-zero integer on the bottom. The next thing I want to talk about is the fraction concepts that you'll be teaching. One of those concepts is the part to whole concept. And these are some examples from our textbook. And we see in the first example that we have a whole circle. And we're going to divide that whole circle into 3 equal parts. And that way you can begin to teach students about fractions. If I want one of the 3 equal parts, that is 1/3. Again, the denominator tells you how many parts that your whole quantity is divided into. And if I have 1 shaded, that's how many parts of the 3 that I'm talking about. A second example is with a whole rectangle. We divided this rectangle into 5 parts. So you can see that the denominator of that fraction will be 5 because it is divided into 5 equal parts. So 3/5 means that I'm going to shade 3 of those 5 equal parts. And we read that fraction as 3/5. Again, this is called the part to whole fraction concept. It's one of the first concepts that we generally use to teach fractions. The second fraction concept that I want to talk about is the fraction quotient. This is simply the division of one number by another. If I said 5 divided by 6, it just means that we're taking 5 and we're dividing it by 6. So 6 does not go into 5, then we will continue on. 6 goes into 50, 8 times, and etc. You could convert that, but that is the division of one number by another. We know that when we divide numbers, 5 divided by 6, this has to be less than 1. Anytime that our numerator is smaller than our denominator, you're going to see that that fraction is less than 1. If our numerator is greater than our denominator, then you should get an answer greater than or equal to 1, if it's 6 or higher in this case. And then another way that we teach concepts is through ratios. Ratio means to compare one amount to another. For example, if I was comparing a ratio of men to women, I could say that that ratio is 1 to 23. So we could write that as 1 to 23, or we could write that 1 to 23. So part to whole, fraction quotient, and ratios. I do want you to know the definition of a unit fraction. A unit fraction is nothing more than a fraction whose numerator is 1. So when we were talking about 1/6, or we were talking about 1/3, or if we were talking about 1/8, all of these are considered unit fractions. Any denominator of the fraction doesn't matter, but it must have a numerator of 1. Now we want to talk about an example about how we write fractions from words into the actual numbers. Write the fraction 53 hundredths with whole numbers. Students, when doing this, may get a little bit confused because they're going to look at the last two things and they're going to put 53 as one word, and then they're going to put it over hundredths. But that's not what this is saying. That hyphen connects the word 3 and the hundredths together, and the word hundredths together. So the correct way to write this fraction is actually 50 over 300. The hyphen joins the words 3 and hundredths and tells us to consider them as a single unit. So that means my denominator is 3 hundredths. My numerator would be the 50. Let's talk about the types of fractions. Of course, the first one we want to talk about is proper fractions. Proper fractions are fractions in which the numerator is smaller than the denominator. So again, an example of a proper fraction would be the fraction 3/4. Just like we said a moment ago, it's important to know that proper fractions must lie between these two numbers, 0 and 1. All proper fractions will lie between 0 and 1. You should be able to identify proper fractions, and you should also know that all proper fractions will lie between 0 and 1. The second type of fraction is improper fractions. Improper fractions are fractions in which the numerator is greater than or equal to the denominator. Example 3 shows an example of an improper fraction. The numerator, 7, is larger than the denominator, 5. We know that improper fractions will be greater than or equal to 1. You see that if I had 5 over 5, we would consider that an improper fraction as well, because fractions that has a numerator that is equal to the denominator is considered to be an improper fraction as well. A mixed number is a combination. It's made up of a number that is made up of an integer and a proper fraction. So an example of a mixed number would be something like 2 and 2/3. We have an integer, which is positive 2. We have a proper fraction. Again, we know it's proper because our numerator is less than our denominator. Since we're talking about mixed numbers, let's talk about how to work with mixed numbers. First of all, let's talk about converting mixed numbers to improper fractions. To do this, I'm going to write the steps down here for you that you'll write in your notes. You're going to multiply the denominator of the fractional part of the mixed number by the integer part. So if I go back to that 2 2/3, you're going to multiply the denominator by the integer part. So this means 3 times 2, which gives me 6. And then you're going to add to it the numerator. And you're going to put that over the denominator that you started with, which is what I have circled, 3. So this would be 2 2/3 expressed as an improper fraction. 3 times 2 plus my numerator of 2 gives me 8 over the denominator that I had of my fraction to start off with. All right, let's look at another example. We want to convert 5 7/8 to an improper fraction. So what we're going to do is we're going to take 8 and we're going to multiply it by 5. That's going to give me 40. Then I'm going to add my numerator to it. 40 plus 7 gives me the 47 that you see here. And then I'm going to put the 47 over the denominator that I had. So we have 47/8. Okay. Let's talk about locating fractions on a number line. Fractions are located on a number line by using the part to whole concept. First, select a unit and then just divide this interval into equal parts. For example, I have on the number line the numbers 0 to 1. In between 0 and 1, I've decided that I'm going to divide this into 7 parts. So I have 1, 2, 3, 4, 5, 6, 7 parts between 0 and 1, equal parts. And if I want to identify 6 of the 7 equal parts, then I'm going to shade 6 parts. 1, 2, 3, 4, 5, 6. This would represent 6 out of 7, and we read that as 6/7. Okay, let's talk about equality of fractions. Here's a simple activity that you may start out with, and that would be by using an area model. By using an area model in which part of a region is shaded, students can visually see how fractions are related to a whole unit. As I've drawn right here, we see that 1 represents 1 whole, and I have divided that into 2 equal parts. 2 equal parts means that I have a denominator that's going to be 2. So I've shaded this in blue to recognize 1/2 and 1/2. So this is really good to let students know how to compare fractions if they're equal. You can see that 1/2 is equal to 1/2 and that 2 halves make a whole. We can see what we have written in red is that I have 3 red segments. They're divided, this whole unit is divided into 3 equal parts. And you can see the difference also in comparing the size of something that represents 1/2 and something that represents 1/3. Students are going to move from knowing that the integer 3 is bigger than the integer 2, but in fractions, when we're talking about parts of a whole, that 1/2 would actually be larger than 1/3. Visually seeing that helps students understand that when we're talking about fractions, that we're talking about dividing a whole into a certain amount of quantities. So if I'm taking this that's in blue, I'm dividing it into 2 parts. So I've taken a whole and I divide it into 2 parts. It makes sense that 2 parts are going to be larger than if I take the same amount and I divide it into 3 parts. So let's talk about what's the definition of an equivalent fraction. What do I mean if fractions are equivalent? This means that they have the same value. You can put it in terms of real world. If you're talking about I ate 1/4 of a pizza, then that means the same thing that if I ate 2/8 of a pizza. Those would be equivalent. But putting in concepts of something the students understand, drawing pictures of that, is going to help them understand it. Equivalent fractions may look different, but they represent the same point on the number line. So if I am talking about the 1/4 and the 2/8, we need to let them know that those are equivalent. Even though they look different, they have different numbers, but they would represent the same amount of pizza. How do you test for equivalent fractions? One of the easiest ways to test for equivalent fractions is to use the cross product. If the cross products are equal, then the fractions are equivalent. If when I cross multiply, I do not get an equivalent answer, then that tells me that the fractions are not equivalent. So the theorem says that if I have two fractions set equal to each other, if when I cross multiply, A times D equals B times C, then they are equivalent. So let's practice these. Example 8 says determine if 3/4 and 6/8 are equal. All we have to do is cross multiply. 4 times 6 is 24. 3 times 8 is 24. And 24 equals 24. So yes, they are equivalent. Use the test for equality of fractions to determine which pairs of fractions are equal. So let's look at example 1. All I have to do is cross multiply. So if I multiply 105 times 14, I get 1470. And if I multiply 42 by 35, I get 1470. So yes, they are equivalent. Example 2, if I cross multiply, yes, -6 equals -6. And in the last example, 35 does not equal 36. So in this case, we would say that they are not equivalent. Very simple test to see if fractions are equal. All right, so let's talk about equality of fractions. One way that we teach this is using a tower of bars. So we're going to click this to watch a video of how the tower of bar illustrates many different equalities of fractions.
Do you want an easy way to create professional invoices? Try it free at skynova.com.
3, 2, 1.
The New York Times calls the holdovers laugh out loud funny.
The National Council of Teachers of Mathematics has cited the numbers 0 and 1 as benchmarks. Often, all we need to know is whether or not a fraction is close to 0 or close to 1. In this video, you will see the importance of understanding fraction symbols for determining when a fraction is close to 0 and if it's close to 1. Let's begin by finding all bars that have just one pair shaded and place them in decreasing order. So here we have 1/2, 1/3, 1/4, 1/5, 1/6, and we go up to 1/10, and 1/12. And we'll just write the fractions down here for this: 1/2, 1/3, 1/4, 1/5, 1/6, 1/10, and 1/12. The shaded amounts of the bars get smaller from top to bottom, and the fractions decrease from 1/2 to 1/12 and get closer to 0. Now, if these bars were continued, the bars with 15 pass or 20 pass and 1 pass shaded, their fractions would be less than these fractions here and even closer to 0. I once did this activity with 4th graders, And they wanted to go further, to bars with 100 parts, bars with 1,000 parts, and one student suggested a bar with 1,000,000 parts. They were fascinated by the fact that the fractions for these bars would get closer and closer to zero, but never equal zero. From such observations, students were able to determine inequalities for unit fractions. That's fractions with a numerator of 1, and explain the reasoning. So let's look, for example, at 1/8 and 1/5. Okay, which fraction is closer to zero? Now this, the bar for this fraction is going to have 8 parts and 1 part shaded. And those parts are going to be smaller than the bar for this fraction here. So this fraction 1/8 is less than 1/5. 1/8 is closer to zero. And we'll start with 1/2, 2/3, 3/4, 4/5, 5/6, 9/10, and 11/12. So let's just put their fractions down here. 1/2, 2/3, 3/4, 4/5, 5/6, 9/10, and finally here 11/12. So the shaded amounts of the bars increase, and these fractions increase from 1/2 to 11/12 and get closer to 1. Now some students might notice the unshaded parts of these bars. These are getting smaller and smaller, and closer to zero. This is an important observation for determining inequalities of fractions such as these, where the numerator is 1 less than the denominator. For example, let's look at the fraction 7/8 and 14/15. Which fraction is closest to 1? Now the bar for this fraction here has 8 parts and 7 parts are shaded, so that's missing just 1 part, 1/8. The bar for this fraction has 15 parts and 14 are shaded, so this is missing a 1/15 of being all shaded, being a whole bar, and 1/15 is less than 1/8. So this fraction right here is closer to 1. The Tower Bars map from the fraction bars materials has blank bars that can be used to model fractions by halves, thirds, fourths, down to 12ths. Fraction bars can be placed on this map or students can color or shade these bars to illustrate or discover relationships. For example, every other bar can be half shaded to show fractions that are equal to 1/2. Similarly, every third bar can be shaded to represent fractions equal to 1/3. And we could shade every fourth bar to show that 1/4 is equal to 2/8, which is equal to 3/12. This map has 2 parts of each bar shaded. At least we started that way, 2 parts out of 3, modeling 2/4 here, 2/5, 2/6. And this shows, if you want to continue shading this, at least it can be generalized that if you have a fraction with a fixed numerator of 2, and the denominators increase, the fractions are going to decrease. And this can be generalized to fractions having a fixed numerator. As the denominators increase, the fractions will decrease. Another relationship students can indicate is to show that as fractions with a fixed numerator of 1 and the denominators increase from 2 down to 12, the shaded amounts decrease and the fractions decrease and get closer to 0. And we can also show increasing sequence of fractions now. 1/2, 2/3, 3/4, so forth down to 11/12. These fractions get closer and closer to 1. Now students might notice that the tower bars is symmetric about a center line. The left half can be folded over to coincide with the right half. For example, These bars have been shaded here. We have the unit fractions decreasing from 1/2, 1/3, 1/4, and so forth down to 1/12. Now the red shaded amount also represents 1/2, 1/3, 1/4, down to 1/12. And other relationships can be determined by considering symmetry. The decreasing amounts of these red shaded paths can be used to show the increasing sequence of fractions get closer and closer to 1. We can use the idea we were just looking at. Now we know that these red shaded amounts decreased, get closer to 0. Since they're used to complete these bars, so we have whole bars right here, since these are decreasing to 0, these shaded amounts are increasing and getting closer to 1. In this video, the decreasing shaded amounts of the bars provides a strong visual image that as the number of equal paths increase, the fractions for one of these paths decrease and get closer and closer to 0. Similarly, the shaded amounts of increasing bars is another strong visual image, showing the fractions whose numerators are 1 less than their denominators get closer and closer to 1 as the number of equal paths increase. Here are 8 more of the 16 games on fractionbars.com. Let's look at hitting Astros.
Okay, I know that was not the most entertaining video. You can definitely tell he's not from South Georgia, but it really is a good example of how tower bars are used to let students compare fractions, and especially about the difference between what 1/8 looks like and 1/12 looks like, which one of those is bigger. So it gives a good example of that. We're going to talk about a test for inequality of fractions. It's very similar. You can see that we have both inequalities here listed, less than or greater than. Again, if you do the cross products, but you compare the inequalities, this will tell you the correct inequality of fractions. So if we look at an example, example 10 says, determine the correct inequality for each pair. Will we do less than or greater than? Again, this is not only going into fractions, but knowing whether you understand which one of those represents less than and which one represents greater than. So if I wanted to see if 4/5 was greater than or equal to 7/9, if I cross multiply, I get 36. Notice we start with A times D. 36 is greater than or equal to 35. That is true. So I'm going to use the greater than symbol. So yes, that would be true. All right, if I cross multiply, A times D, 5 times 3 is 15. Is 15 less than or equal to 16? Yes, that is true. Is 20 less than or equal to 21? Yes, that would be true. And 3 times 7 is 21. Is 21 greater than or equal to 20? Yes. So this is how we would determine. We simply do the cross products. Very important concept that we're about to talk about, and that is reducing fraction to lowest terms. When a fraction is converted to the fraction that has the smallest numerator and denominator in its collection of equivalent fractions, it's said to be reduced in lowest term. The only whole number that divides the numerator and denominator without a remainder of a reduced fraction should be 1. If you can divide the numerator and denominator by any other number than 1, then that fraction is not reduced. If the numerator and a denominator of a fraction are divided by their greatest common factor, we've already talked about the GCF, the greatest number that we can divide both fractions by, then we're going to say that that resulting fraction is a fraction that's in simplest form, and the fraction is said to be in lowest terms. Two numbers are considered what we call relatively prime. If you're looking at those two numbers and there's no other common factor other than 1, then we say that they're relatively prime. We bring this into this lesson because if the numerator and denominator are relatively prime, then you know that your fraction is said to be in lowest terms. No matter what problem that you're looking at and you're dealing with fractions, you always want to reduce them to their lowest form. You're never going to leave an answer that's not reduced. There are two methods of reducing fractions. One of those is to divide out the common primes, and the second way is to divide out common factors. So as we start to teach this about reducing your lowest terms, it's very important that our students know how to do this. Again, here's like a helpful hint. Sharing a catchy video with songs helps them learn or remember to reduce their fractions. So I'm going to share one that I found from Number Rock.
I just found an app that can get you a plus in any class. Just upload your assignment and
To convert to fourths to simplest form. Write out all the factors of 2 and 4. The greatest common factor is 2, so divide them both by 2. 2 fourths equals 1/2, and here's what we do. To convert to the simplest form, we gotta find the greatest common factor. Then take that numerator and denominator and divide them by that common factor. To convert 4/12 to simplest form, write out all the factors of 12 and 4. 4 is the greatest common factor, so divide by 4 fourths to see. 4/12 equals 1/3. To convert to the simplest form, we gotta find the greatest common factor. Then take that numerator and denominator and divide them by that common factor.
Check it out now. Simplest form and lowest term. The synonyms which you may have heard are two different phrases or words. The definitions are uniform. Using a geometric model can help us learn what's happening when converting simplest form. A rectangle shows 5/15. The GCF is 5, which means no greater number can divide both 15 and 5. So divide both by 5. Get 1/3 as lowest term. It's so boss being a nerd.
To convert to the simplest form, we gotta find the greatest common factor. Then take that numerator and denominator and divide them by that common factor.
Common factor.
Okay, so there's so much stuff on YouTube, that you could find for students to look at. So I'm sure that while you're teaching, you're going to be incorporating a little bit better videos than I did in that first one. All right, so let's talk about how to reduce fractions to lowest term using the common primes. What you want to do is you're going to write the numerator and denominator as a product of primes, and you simply cancel out all the common factors, and then whatever you have left in the numerator you multiply together, and whatever you have left in the denominator you multiply together. All right, so let's look at an example. If we do 16 and we write it out as a product of primes, that's 2 times 2 times 2 times 2. 20 is 4 times 5, so 2 times 2 times 5. So we mark out all common factors, and whatever we have left we multiply back. 2 times 2 is 4. I only have a 5 on bottom. So since 4 and 5 are relatively prime, meaning that I don't have any other factors that I can divide 4 and 5 by other than 1, then we say that 16/20 reduced to its lowest terms would be 4/5. Again, anytime you deal with fractions, you want to make sure that they're reduced to lowest terms. The second way is to divide out common factors. This way you're going to mentally divide the numerator and denominator by a factor that is common to each. It's not necessarily the largest or the greatest common factor. Sometimes students don't know what that greatest common factor is, but they may recognize that the fraction is even, so they know that it can be divisible by 2. But you just keep continuing the process until you get to the point where the numerator and denominator are relatively prime. And this is what a lot of students are going to do. So if I reduce 18 divided by 12, again, I've started off by they're even. So students may not know the greatest common factor, but they do recognize that they're even, so we divide them by 2. So 18 divided by 2 is 9, and 24 divided by 2 is 12. So I get 9 twelfths. Well, we're going to continue on. We know that 9 and 12 is divisible by 3. So 9 divided by 3 is 3. 12 divided by 3 is 4. Since 3 and 4 are relatively prime, there's no common factor other than 1 that I can divide them by. We know that 18 24ths, reduced in its lowest form, is 3/4. All right, so let's do some practice with reducing fractions to its simplest form. 9 15ths would reduce to 3 and 5. 9 divided by 3 is 3. 15 divided by 3 is 5. When I look at number 2, I think of a number that I can divide 25 and 30 by. Of course, I'm doing the common factor. I know that they're both divisible by 5 because they end in 5 and 0, one of our divisibility rules. So 25 divided by 5 is 5. 30 divided by 5 is 6. 5 and 6 are relatively prime, no other factors other than 1, so that is reduced. 7 over 14, I can divide both of those by 7, so that reduced fraction would be 1/2. That would be a fraction in lowest terms. And then our last one, since 7 and 15 are already relatively prime, actually 7 15ths is already reduced. There's no number that I can divide 7 and 15 by other than 1. I do want to talk before I show you the references about a slide that was skipped in this presentation, and that was going back to converting improper fractions to mixed numbers. This should have been right after we started talking about the different types of fractions, the improper, the proper, and the mixed numbers. So right after that, in your notes, you'll see that I ask you to convert improper fractions to mixed numbers. To do that, you're going to divide, and this is what you should write in your notes, that you're going to divide the numerator by the denominator. And in example 5, and I'm sorry my handwriting is not great here. In example 5, I ask you to convert 5/3 to a mixed number. So we're going to divide that out. It is 5 divided by 3. The numerator is inside the division symbol, 3 is on the outside. So 3 goes into 5 one time, then I'm going to multiply. 1 times 3 is 3. I'm going to subtract that product, and I get 1, and this is going to be my fraction part, 1 2/3. The next example that I gave you was example 6 in your notes. And again, I'm having to backtrack because there was a slide that was skipped. In example 6, I ask you to convert 46/9 to a mixed number. So we're going to take 9 and we're going to divide 46 by that number. So 9 is our denominator. It goes on the outside. So 9 goes into 46 5 times. 5 times 9 is 45, so I'm going to subtract that product and I get a remainder of 1. So we're going to put that remainder as 5, and again, this is our fraction part, 1 over our denominator. So the answer to example 6 is 5 1/9. I apologize for not putting that in the correct place or adding it to our PowerPoint. We will correct that. And here are our references, which are included in your notes.